My name is Dave van Zanten. I'm working at Fermilab in the capacity of a associate scientist. I'm going to talk about the NQI, the National Quantum Initiative Center, called Superconducting Quantum Materials and Systems Center. We are not a company, but we do make hardware, quantum hardware. And so that's my title slide, in fact. So I will discuss a little bit what the NQI is, or our NQI is, and I'm going to focus on a couple projects that I'm personally involved in. Besides being an associate scientist, I'm also the lead of the quantum measurement team there, and I'm deputy head of the testbed system. I will discuss what the quantum testbed, also known as the quantum garage, is. And as Fermilab, we're being an NQI, we're not just a Fermilab. We are actually a big collaboration of currently about 34 partner institutions with more than 500 collaborators. And the whole goal of this NQI is to tackle really the understanding and elimination of the decoherence mechanisms in superconducting quantum systems. That can be a qubit or that can be a qubit, and I will come back later to that. Also, we want to take advantage of our superior systems and then apply them, for example, to things like quantum computing and sensing. So we have a mission-driven roadmap, which starts with the foundations of understanding the materials that we're using in our quantum technology, then demonstrating that by that understanding, we can make actually better qubit devices or qubit devices. Obviously, we want to make something out of it, so we make quantum hardware. So we need to integrate this into QPUs, for example, either two-dimensional or three-dimensional QPUs. And then, everybody knows that with scaling, you cannot, get around the cryogenics issue. So we're also deploying large cryogenic systems. In Fermilab, we had a lot of decades of experience in big cryogenic systems. And then we are not only a hardware development, not a company, effort, but we also look into how to take advantage of quantum systems to do quantum computations. So that's our roadmap. But yeah, let's start at the first 2 years of our effort, which is really understanding the decoherence principles and where the loss channels come from. So that being a big NQI with a lot of partners basically means that you have a lot of resources at hand, and we can take qubits that are being manufactured by commercial companies. In particular, Rigetti, who is a partner of us, we can take their qubits and we can use all those tools, some very basic, but some very, very advanced and very exotic tools. We can use those to understand where the decoherence comes from, what the material properties of these qubits are. And from that first 2 years, we basically understand that in typical 2D qubits, the niobium oxide is one of the bigger contribution to single qubit devices. Now, once you know that, you can, of course, tackle that. You can change your fabrication procedures to make better devices. And to do this, we set up this National Nanofabrication Task Force, which comprises out of 4 foundries. Each of these foundries are producing literally the same type of qubit. It's a uniform qubit device. Every foundry is producing those. The only thing that really changes is the fact that they're on a different location. They have a different tool chain. And maybe they have different capabilities in the terms of the RI base pressure, or maybe they're using silicon instead of sapphire, etc. So by using this approach, we were able to really beef up the coherence times by by an order of magnitude over a 1 year time period. So that's a rapid increase in just one time period, one year. So this slide here, I don't understand why my pointer is not working. But so this slide here with roughly 200 microseconds T1 times for qubit devices is actually a little bit old. Over the last 6 months, we have actually doubled that, and we're now consistently reaching about 400 microseconds for our T1 on these qubits. And that's really because we're following this encapsulation strategy of replacing the niobium oxide with, for example, a thin layer of tantalum or a thin layer of aluminum, etc. So one of the projects where we really shine as being a collaboration, besides this one, of course, is the round robin project. We don't only distribute out our fabrication, we also distribute out our measurement. The whole idea of this project is that we take a single qubit device and we're measuring at different sites across the world. Some are in Europe, some are here in in the United States, and we want to establish how consistent these results that you're measuring are across the different sites. And then if you're even able to unify that, for example, let's say that we find differences, are you even able to address, make all these systems identical and thereby actually literally getting the same value for all of the different test beds? So that's one of these questions that we want to answer. The essential part here is basically that we have this single device being packaged. Nobody really knows the content. You're just measuring it. You're measuring it using a semi-automated measurement procedures, and basically you don't report the data in group meetings. It just goes into a big black box, and then later on you will see it. So currently we have about 8 or 9 different test beds that are participating, and actually per week, no, not per week, but quite often there's people being, different test beds being added. So we're growing rapidly. I think I'm going fast through my time. I don't know how I am. So another effort, and I think that's that's the coolest one currently for me because I'm heavily involved in that, is the development of a SQMS 2D quantum processor. So it's great if you can improve the coherence time. However, typically what people report when they're talking about improvement of coherence is a single qubit coherence. However, we all know that if you start to connect this into an integrated system, you compromise a lot. And we want to know where this compromise comes from. Like, why do you need to compromise it? Is it not possible to make a qubit or an integrated system without at all compromising T1 by being smart about how you connect it, right? So there's a lot of work done by the companies, by IBM, etc. But we do want to take we want to try this for our own as well. So we are very lucky and very grateful that we have a great collaboration with Rigetti, who can supply us already a 9-qubit QPU system simply for us to get our quantum testbed going. And all the development of the hardware, the room temperature hardware, the cryostat hardware, etc. And then sort of tied with the improvement of the 2D QPU, the 2D qubit timeline, we want to start moving that technology from T1 improvements into an integrated system, meanwhile also understanding how we can not compromise T1. And then finally, in the end, we want to have a 36-qubit QPU operational at Fermilab with open source quantum hardware like the CIC platform that's also being developed at Fermilab, and basically used by our researcher to do algorithm search. The benefit there also is that we can basically control the full calibration and the pulse control all ourselves, and we can customize that. All right. One thing where I think that what I think is very interesting as well is kind of addresses the question about the scaling of quantum systems. 2D qubits are amazing. They're really nice, and we put great progress into making them better. But they will have a connectivity issue if you start scaling them. So there's a lot of other questions. One system that kind of mitigates that, not entirely, but kind of mitigates that, is a 3D qubit system. And with a 3D qubit system, I literally mean storing quantum information into harmonic oscillators that you create by using 3D superconducting resonators. And very conveniently, Fermilab holds the world record into coherence times for those 3D resonators. Those resonators are used into acceleration beamlines. This is where you know Fermilab from. So we basically take benefit of this decade's improvement of these resonators, and we take benefit that they have now 2 seconds lifetimes. So if you are able to encode quantum information in those systems, you gain in terms of lifetime. But moreover, you don't need to encode anymore in two states. So you don't need to encode Q bits. You can encode Q dits. And that basically means that you get a bigger Hilbert space per unit, and that improves your scaling a lot. All those different Q dits can still be living in the same kind of 3D cavity system. They're just at different frequencies. So this system allows you to frequency multiplex your Q dits, which is another gain in terms of Hilbert space per line. And then, so finally, you get a much bigger Hilbert space per control line, and that allows us to scale these systems back better. All right, so this shows some data about how we can preparate single photon Fock states, or 2 photon or 3 photon Fock states in these linear cavities. And the coherence times that we initially got were roughly 1 millisecond, so it's far not close to what I promised of 2 seconds. But over already the course of a half a year, we've improved that by by factor 5. So we start to understand very carefully where these losses come from again in the system, and we're really mitigating them and resolving them. So it's a very promising activity. And this all is based on well understanding and good fabrication of qubits and understanding of 3D cavity systems. All right, so for the 3D QPU system, we do have a little roadmap that requires a different change in the architecture, a little change in the architecture. You cannot necessarily encode all different modes onto a single qubit, all modes on a single qubit, but you can play tricks, and that does allow us to basically make something like a quantum random access memory and use that in our architecture. So finally, I think I'm actually pretty fast. So lots of questions. Finally, I want to take a little bit of time to discuss the Quantum Garage, which is our new quantum testbed. And I think it was about 4 weeks ago that we had a big opening of our Quantum Garage at Fermilab. And we had the governor and folks from Congress all joining us in doing a nice ribbon cutting. So this Quantum Garage is, in fact, we have, it gives us 8 XLDDRs, each running 8 different experiments. So that allows us to run about 64 different experiments simultaneously. And this serves 6 scientific trusts. So this is not only 2D qubits, this is 2D qubits, material development, cavity development, 3D cavity qubit development, 2D QPU systems, and physics and sensing. So it serves a lot of scientific effort. Finally, to organize this all, it's ran by a dedicated team, dedicated measurement team that built up the experiments to execute these measurements very carefully with a lot of scrutiny. And it gives us a lot of accountability for our results that we're publishing. And then finally, all this hardware is maintained by an instrumentation team who, on a daily basis is pushing the frontier on making better control hardware and making better hardware filtering hardware for inside the DR, for your signal conditioning, for your thermalization of your systems, etc. So with that, I would like to thank you, and I want to acknowledge the guys here in the picture on the top left, who are the colleagues that I regularly see who are working at Rigetti, and their system is there visible in the center. Thank you very much.
Indeed, we have time for questions.
Yes.
Hello, thank you for the very nice talk. My name is Hao Ting from E3 Taiwan. Would you mind to elaborate a little bit more on the roadmap for the 3D qubits or qubits? Thank you.
So when I mentioned that you can encode quantum information into 3D cavities, and you can, in fact, encode one qubit into a single mode in a 3D cavity. So a 3D cavity can have, of course, multiple modes, and each one of those can serve as a Hilbert space for you. Now you could imagine that you can control all those different modes using a single ancilla qubit, but that's not possible, because that single ancilla qubit is gonna couple all those different modes with some residual coupling, which is very similar to residual ZZ coupling in 2D qubits. So that generates a state-dependent problem. And to mitigate that, or to get around that, you need to make sure that the coupling between these different modes is not based on a dispersive coupling, but is in fact, it's a different type of coupling. It's more like a beam splitter coupling. And the beam splitter coupling does not couple all these different modes together. So you don't get this residual ZZ or state, you don't have this state-dependent problem. So that is right now really driving our, determining our roadmap. So we have these cavities. Currently, we are able to go up to 5 milliseconds, 6 milliseconds lifetimes for these cavities, for the quantum states inside these cavities. We really want to go towards about 40 milliseconds at the end of this year. But however, then to scale up the system, we really have to tackle this change in architecture, where you say, okay, instead of directly encoding quantum information into a single mode, we're gonna encode quantum information into a single mode. That quantum information is then going to be swapped inside the quantum access memory, where you kind of store it, and then you do on computations on different modes, etc. And like this, you build up your coherent state. in your entangled state. So that is basically what you see here in this roadmap. You say, okay, we can make these quantum systems working in SRF cavities, these long-lived cavities. We can make good photon states in there. We're working on universal QDIT control right now using what's called SNAP gates and ECD gates. And then somewhere next year, we want to be able to start doing those swaps across the using a coupler in a sort of smaller system, and then finally, at the end of 2025, roughly, we want to have multiple of these units swapping quantum information around. Does that sort of address your answer?
Yes, thank you.
All right.
Any other questions?
Mickey Slamp with the Great Plains Network. How does your foundry interact with other foundries around the country that are not a part of your project? So I'm working with an NSF-funded foundry, and so I was curious if you're related to it, if it's not a part of your direct program.
As far as I know, we do not necessarily have already any interactions, but I think we maybe should. So maybe we should discuss this.
Talk.
Yeah, thank you for the nice talk. I'm Shintaro from Fujitsu. I'm just wondering, you try the same chip design for all the institution, and what the origin of the difference? Do you know? Do you have any idea origin of difference in the coherence time across the laboratory?
Between the different foundries?
Yes.
Actually, they're pretty on par. So there is some difference related to. Sorry?
A lot of errors. So
yeah.
Very similar, you think? You believe?
Yeah. So on average, So on average, basically, if we do a single run, we do see comparable data between the different foundries. Sometimes, the differences are, let's say, within the error bars. Okay. Sometimes we do see differences. And that basically, triggers then a good material study again. So the nice part is that this effort and this effort, I've broken them down into different slides. But actually, they are part of a bigger round, a bigger feedback cycle where we do this study, we devise new strategies of making the qubits, and then based on differences that we observe, we go back to this again and figure out where the differences come from, and that is that's a little machine that cranks constantly. So yeah, there's sometimes differences, and sometimes we don't understand, but overall, I would say in about 80% of the times, we kind of see uniform results across the different foundries.